Hello class and welcome to the session. In this session we're going to be talking about a unique IC that was developed years ago called the 555 IC 555 IC 555. It's a very common IC, we've seen this earlier. In this case it's using to run a counter to shift the outputs between these three outputs. So you can have three different LEDs cycling between 1, 2 and 3. How does it precisely maintain time? Precise maintenance of time is based on the resistor and capacitor values. Now earlier we saw about how we could talk about duty cycle when we talked about an inductor and a capacitor as a tank circuit that can oscillate. But in this case, how does a resistor and a capacitor maintain time? In other words, a capacitor is like a spring. Since resistor is a current limiting source, now it reduces the potential or restricts the potential that goes to the capacitor. The time taken for the capacitor to charge itself is controlled. The moment the capacitor is fully charged, that charged potential could be used to trigger another part of the circuit, which would discharge it. And again, it would go back to the charge cycle. So the oscillation between charging and discharging is precisely timed by the value of the capacitor. In this case, it's an electrolytic capacitor that you see. So what controls the charge discharge cycle? The current that is restricted by the resistor. So the combination of the resistor combined with the capacitor controls the time of the charge discharge cycle of your the charge discharge cycle of the capacitor controls your IC to give you precise time of say 1 second or 2 seconds, I mean 1 hertz or 2 hertz that is required to drive an LED board like this, LED outputs through these transistors. So it's a very simple IC. Now let's look at how technology has evolved and how our forefathers have developed this IC using all the fundamentals of electronic components that we have seen till now, like your operation amplifiers, your flip-flops, and your transistors. Okay, let's look at that right now. So this is the internals of your typical 555 IC. Now let's look at it. As you saw, it's a simple small 8-pin IC. Your first pin is your ground, your second pin is your trigger for your input, your third pin is your output, 4 is to reset it, 5 is the control voltage, 6 is the threshold level set, 7 is to discharge, and 8 is your power supply. So this is your plus and this is your ground power supply to operate your 555. So this is an internal circuit of your 555. So you have your transistor to drive that's there to control the discharge line, and you also have your output controlled through another transistor driver, and you have your flip-flop to change between on and off and cycle to control your output stage. Now let's look at exactly what happens in the process of having the internals to see the workings of the circuit. Now a typical application of the circuit would be to have a square wave or a pulsed wave generated. In this case, it's a basic astable circuit. In other words, it's called an astable multivibrator. In other words, it toggles between on and off. I can control how long it's going to be on and how long it's going to be controlled off. In other words, it's called the duty cycle. The duty cycle just says what percentage is it on and what percentage is it off. Controlling your on time and off time is called duty cycle. It does not matter the frequency, at what percentage is on and what percentage is off. Example, it's on for 2 milliseconds and off for 1.5 milliseconds. This would be a percentage. What is 2 and this is 2 plus 1.5, 3.5 divided by 2. 2 divided by 3.5 would be the percentage of on, to 1.5 divided by 3.5 would be the percentage of off. So it's all about identifying the on time and off time, and that's your duty cycle, and that's what we call the on and off time of a astable multivibrator. What controls this on and off time is your value of capacitance and your resistance. Now, how do you control this resistance value and how do you control this capacitance value? It's all about putting the right capacitor and resistor to be able to get the time required to charge up your capacitor and the time required to discharge your capacitor. So your capacitor is discharged and charged through resistance. So that time is all that your 555 IC requires to be able to operate within that range. Now there's a formula for it. Now if you look at a stable multivibrator using a 555 as an oscillator, the time required for T1 on cycle is 0.693 into R1 plus R2 into C, and this is in resistance and this is in capacitance. And you have formulas that you can help you to determine. R is in resistance is in ohms and capacitance is in farad. So if it's in microfarad, you have to use it. You got to convert it into farad using the conversion of 10 to the power 3 or 10 to the power 6 appropriately. So the total time, the frequency of oscillation, frequency is inverse of time, and that's the formula that's derived. It's 1.44 by R1 plus R2 into C. So if I want a particular frequency, I control the values of R1, R2, and C to get a particular frequency. In this case, we saw the circuit. It had a frequency of about 1 Hertz. So every second you can see the output toggle between the 3 outputs of your output LEDs. So now you can have, these calculations are pretty straightforward. You can do it in a matter of seconds using a scientific calculator. Now let's look at how you have control over the way this is precisely timed. So you can have improved versions of it. In other words, we have a diode that precisely controls which current flows. This current goes through one resistor. In other words, I can control the on time and off time. So the one current to charge it goes through one resistor, the discharge goes through another resistor, and it's controlled by 2 different diodes. So the forward current goes through one resistor to R1 and discharge current R2. So you can precisely time your R1, T1 time and T2 time. So you can have the circuit. In other words, IC is a common IC. What you do with the IC has different applications. Now you want a precise control where you want it exactly 50% time is on, 50% off. In other words, T1 is equal to T2. In that case, you can have it designed this way. One resistor, combine the inputs to your trigger, and then you have your feedback, which is R2, and that is fed back into your trigger line. So you have a precise control. In other words, output drives the input, so the frequency is controlled exactly, and the frequency is 1 by 0.693 to 2 into R2 into C, and the output is in Hertz. So you've seen the circuit. Let's look at it, how it is in working as a simulator. Now this is a simple circuit. You have your output at 5 volt, and the voltage to your capacitor is shown here. It's running at about 6.673 volt, and your power supply is fed from a 10 volt power supply. Yes. Now this circuit tells you how this output line toggles between on and off. In other words, when it's green, it's on. When it's low, so this is your output. It's a square wave. The on time is high, the off time is low. You can change the values of this resistance and capacitance and use external circuit to be able to change this timing. So the formulas that we calculated earlier, the theoretical calculation and the simulated values would match, and that's the difference between how do I precise example. I want the light to blink faster. I could have this resistor as a variable resistor. So when I want to have it as a variable resistor, I can control this frequency at which it blinks, and that's how I can control the flickering rate or the output frequency of your 555 IC. So is it only suitable for low frequencies? The answer is no. It can do a decent high frequency also. In this case, it's running at about 159.2 Hertz. So 159 times in a second, the output changes between on and off. Yes. Now let's look at another circuit. In this case, it's called a monostable multivibrator. In other words, it does not always change states. The output constantly stays at 0 volt. Can you see it dark out? Okay. Now, the moment I give a trigger, I gave my trigger. I brought it low for 1 second. I mean, a very short period of time. I brought it low. When I brought it low, the output had a precise on time and off time, and then stays off. In other words, if I give a trigger, the output would go on, stay on for a short period of time, and go back low. Why do I need this circuit? You might say, I give a small trigger. If I give a trigger, the output will stay on only for a fixed amount of time. Let's look at a pump. You notice pumps have starters, and starters example is this. It could be a star delta starter. I connect it on star, wait for the motor to pick up speed, and then I switch it on to delta. Or if I have a capacitor based start for a pump, I turn the motor on and I hold the start button for like half a second and then turn it off. Now I want to control this pump using a controller. Instead of me hitting the start button when the water level goes low, I want another controller to hold the start button for half a second. That's when I need a monostable multivibrator. So the small trigger required to activate your pump would come in from your microcontroller. It goes on, it goes off. The moment that happens, your starter will get the input, it will stay on for half a second and go back off. So that's possible. So as long as I pull it low, doesn't matter. The output only turns on and turns off for a precise time period. This is possible with a monostable multivibrator. In other words, I give a trigger, I can hold the start button for infinite amount of time, but yeah, that would damage the motor in the case. So to avoid it, the output of the monostable multivibrator would hold the start button down only for the precise time. Example, if the manufacturer says it's good to hold it only for half a second, that's the time it requires to pick up speed and the motor start running. That's what the output would do. So it has a lot of applications in industry, and this is a simple application I gave you as an example, and there are many other examples we can talk about. Now let's look at another circuit. This is a square wave generator. Now this graph shows you the voltage and current inside your capacitor and how the voltage rises and falls, and that is what controls your trigger input. And that trigger input is fed back through a 10K resistor to input, so you're precise on time and off time. We saw the circuit earlier, now we see the circuit in working. In other words, it's not showing the internals of the circuit, just the external connection and how the current flows between your feedback loop back to your input to trigger it, either to ground it. I mean, it's either through the capacitor to the ground, or when the threshold is set, it triggers your input and turns on your output. So this is a square wave generator using a 555 IC. Let's look at another circuit. Now you might say, can I use it for something else? Yes, traffic lights. This is an interesting circuit. You remember this component, a ring counter? Now look at this output. Every time, this is now my square wave generator. In other words, this is a generator which is generating a fixed frequency, and that input is fed into my ring counter. So my ring counter is switching my outputs between, it's counting 1, 2, 3, 4, 5, 6, 7, and it's going back in a loop. So if you look at it, can you see the green line following? Every time I get a pulse, the ring counter increments the output and sends it to the next output line. And this sequence is used by a few gates to control the green light for a particular amount of time, your orange light for a particular amount of time, and a red light between two different lanes. And this is done with a simple circuit realized with logic gates, in this case 1, 2, 3, 4 OR gates, one ring counter, a 555 IC, a couple of resistors, and your capacitor. And these LEDs could be driven by your power supply, and that is not shown here in detail, but in this case we're talking about a 5 volt power supply. In case you want to drive a bigger LED or a bigger bulb, then you need to use this to drive a transistor maybe, and that transistor would drive or a SCR to drive a heavier load. So now this is a practical circuit. So this fixed frequency, what is the frequency of this? It's the time cycle is about 1.2 milliseconds. Yes, and that output is fed into, it's going to be between 5 volt and 0 volt. Can you see the data below? It's 50 nanoamps or 0 amps, and this output from your 555 IC is fed into your ring counter. Your ring counter keeps switching these outputs all the way, all the outputs. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 outputs, and those 10 lines keep circling because this is a ring counter. That's what it's meant to, that's designed to do. And this outputs using these gates can be used to precisely control its output to these 3 LEDs using these logic gates. So you can see the logic gates working. You can see the LEDs of this traffic light working. You can see there are some current limiting resistors to the ground. So these are LEDs having a common resistor. So for example, let's look at it in reality, what it will look like. So I could have a single LED that has 3 different colors. Let's look at it in a realistic circuit. So here I do have a 3-color LED. So I could have red, yellow, and green in one LED capsule. So there are 4 pins. 1 pin is common, there are 3 other pins for the 3 different colors. Now this is possible to have the circuit that we talked about, the 555 timer running a ring counter, and then we talked about the logic gate IC in between, and that can drive these LEDs using these current limiting resistors to switch between red, yellow, and green with a precise time, like a traffic light. So in this case, we had two different lights, three color LEDs. So you had three different LEDs actually separate, but this is a single package which has got three different LEDs inside it. So this is how a simple 555 IC like this one, not very expensive, just might cost a few rupees to be able to do exactly what you require in having a particular task done, like as we saw a practical case of a traffic light. So 555 ICs, simple IC, which developed with the development of transistors. Transistors developed op amps, and op amps gave about the development of circuits like these, where it's like the PN junction is developed. So you have the entire circuit of a 555 IC into a single package. Then you talked about ring counters, how they were realized with logic gates, and that's encapsulated into a single IC. So these are integrated circuits, and that's your clock input. You have your outputs of your ring counter switching. So each output is going high, and the switch, it goes high, and this is the logic gate controlling it. So, and I was able to combine all those inputs. Any one of those inputs are coming in, the output is going out. That's the reason they're using the 4-input OR gate. Either this any one is on. So anytime it's between 6, 7, 8, 9, this output is on. So it's like more or less controlling the time delay required for the different lights to go on. So this one controls the time required for the green light here, and these 4 lines control the green light here. So it's a simple circuit of how I could use a 555 IC to control time in a realistic application. So, and if you have any other questions on how you could practically build a circuit with a 555 IC or any of the topics that we saw earlier, feel free to reach out to me and I'll help you to get you the list of components. You can use the software that we talked about. This is online simulation software to be able to simulate your circuit, fit the values of resistors and capacitors, and in case you make a mistake, the software will tell you exactly where you went, what went wrong, and based on your learning, you can have the circuit fine-tuned, and once you know for sure it's going to work, you can be able to go and build a circuit and have it realized in reality.